Hi everyone, welcome back to our multi-agent reinforcement learning series. Today marks an exciting milestone in our journey. We are diving deep into the architectural foundations that make multi-agent systems work. Before we dive in, let me get a quick show of hands. Who has tried to implement any multi-agent system since our last episode? Send some comments if you run into coordination problems. Okay, perfect. Those coordination headaches you experienced are exactly what we are going to solve today. Remember, in our first episode, we established the fundamental concepts and challenges of MARL, and today we are going to explore how researchers have tackled these challenges through three distinct design paradigms. Think of today's lecture as your roadmap to understanding not just what algorithms exist, but why they exist and when to use them. We'll be covering everything from theoretical ideas to practical implementations, from centralized guard controllers to completely independent agents. By the end of today's session, you will have a comprehensive understanding of the entire MARL landscape and be equipped to make informed decisions about which approach to use in your own projects. Now let me walk you through our journey today. We'll start by examining the core problem landscape, the fundamental challenges that every MARL system or algorithm must address. And then we will explore three major paradigms in order of decreasing centralization. Each paradigm represents a different trade-off between performance and practicality, and we'll see concrete algorithms that embody these philosophies. Before we dive deeper into solutions, let's understand exactly what we are going to solve today, okay? Every single MARL algorithm, regardless of its complexity or sophistications, is fundamentally trying to address these two core challenges. The first one is non-stationarity, and the second one is scalability. These two challenges are in constant tension. Solutions that address non-stationarity often require centralization, which hurts scalability, and solutions that improve scalability often sacrifice the ability to coordinate effectively. So every MARL paradigm represents a different way of navigating this fundamental trade-off. Now let's examine our first paradigm, CTCE. Centralized training, centralized execution. I call this the guard controller approach because it treats the entire multi-agent system as if there is one controller making all decisions. So the core idea is elegantly simple. Why fit the complexity of multiple agents when you can just treat them as one giant meta-agent? So instead of having individual agents with their own policies, we can learn a single policy that controls all agents simultaneously. This approach has two major research directions. First is joint action space method, and second is multi-agent MDP methods. So here's the key trade-off. CTCE offers maximum performance potential because it can find truly optimal joint policies with complete coordination. However, it comes at the cost of minimum scalability due to the componential complexity we discussed earlier. And in practice, CTCE methods are primarily used as theoretical upper bounds. They tell us what's possible if we ignore computational constraints. Okay, now let's dive deeper into the first approach within CTCE, joint action space methods. This is perhaps the most conceptually straightforward approach to multi-agent learning, which makes it an excellent starting point for understanding the fundamental challenges. Okay, the approach is beautifully simple. Instead of having separate queue functions or policies from each agent, we learn a single function that maps from the global state to the joint action space. So instead of learning each queue functions, we learn one queue function that tells us the value of every possible combination of actions. And this approach has several attractive properties. First, it completely eliminates the non-stationarity because there is only one learner. Okay, it also provides theoretical guarantees of finding optimal joint policies, assuming sufficient exploration and infinite time. So here's the fatal flaw, that's exponential growth in joint action space size. Okay, let me give you a concrete example that will make this crystal clear. If you have 10 agents, each with only 2 action choices, you are looking at the 2 to the 10th power, which is 1024 joint action per state. And action selection requires evaluating all of these possibilities. Notice this isn't just a storage problem, it's fundamentally a computational bottleneck. And this exponential growth means the method can only handle toy problems with a handful of agents. This limitation is precisely what motivated researchers to seek other paradigms, right? Okay? Now let me show you exactly how centralized Q-learning works and why it fails in practice. This algorithm is the most direct application of joint action space method and perfectly illustrates both the appeal and the limitation of the CTCE paradigm. Okay, the algorithm maintains a Q table where each entry represents the expected future reward taking the joint action in current state. And the update rule is identical to single agent Q-learning, but now we are updating values for joint actions. So the update rule, okay, this equation, notice that the max operation is now over the entire joint action space, not just the individual actions. And for action selection, we compute the best action where the A represents the joint action of all agents. This gives us the optimal joint action, ensuring perfect coordination actually. But now let's return to our earlier example, 10 agents, 2 actions, and every single action selection requires 1024 evaluations. This exponential growth makes the method fundamentally unscalable. So that's the reality, okay? The second approach within CTCE is multi-agent MDP method. While joint action space method focuses on the algorithm aspect, and MMDP method provides the theoretical framework for understanding multi-agent problems as extensions of single-agent MDPs. The fundamental insight is that we can formalize multi-agent problems by expanding both state and action spaces. This formalization is theoretically elegant because it allows us to apply any single-agent RL algorithm directly into MA settings. Okay? The profound significance of this framework is that it mathematically proves multi-agent problems are essentially single-agent problems, only with expanded spaces. Theoretically, any single-agent RL algorithm can be applied to multi-agent settings. However, the challenge remains the same. The exponential complexity problem still hurts us. Okay? Now let's see MMDP formalization. This formalization is elegant in its simplicity. We define a joint state and the joint action and the transition function and accordingly the reward function of the entire system. And this formalization is significant because it establishes that multi-agent problems are, mathematically speaking, just single-agent problems with expanded state and action spaces. Any algorithm that works for single-agent RL can theoretically be applied to multi-agent problems using this framework. While this formalization is theoretically sound, the exponential growth in complexity makes the centralized approaches computationally intractable for realistic problems. Okay? If we can't centralize everything, maybe we can find ways to get most of the benefits of centralization while maintaining practical scalability. Okay? This brings us to the second paradigm, CTDE, centralized training, decentralized execution. I call this the learn together and act alone approach, and it represents the dominant paradigm in modern MARL research. The core insight is brilliant. What if we could get the benefit of centralization during training while maintaining the scalability of decentralized execution? During training, we can afford to use more computational resources and global information because we are not operating on the real-time constraints. But during execution, we need agents to act independently using only local information. Okay? This paradigm has spawned 5 major research directions, each addressing different aspects of the centralized training challenge. And this paradigm has enabled breakthrough results in complex domains like StarCraft 2, multi-robot coordination, and autonomous vehicle fleets. It's the foundation of the most state-of-the-art MARL systems used in practice today. Okay, let's start with the first one, value function factorization, which offers an elegant solution to the scalability problem. And value function factorization tackles the core challenge with an elegant decomposition idea. That is, break down the intractable global Q value into learnable local utility functions. This approach works for learning individual utility functions for each agent and then learning a mixing function that combines these individual utilities into a total value. The key insight is the individual global max principle, IGM principle. This principle states that if we can ensure this equation, then decentralized execution becomes optimal. In other words, if each agent independently maximizes its local utility, then the result should be a global optimum. Okay, this is powerful because it enables truly decentralized execution. Each agent can act independently using only its local observation and utility function without needing to coordinate with others or access global information. Yet during training, we can use global information to learn a mixing function and ensure proper coordination. Okay, so the challenge lies in finding the right balance between expressiveness and maintaining the IGM property. Okay, a simple additive mixing function may clearly satisfy IGM, but may be too restrictive for complex coordination patterns. On the other hand, a completely general mixing function might be expressive but could violate IGM, leading to suboptimal decentralized execution. So this tension has driven significant research into different mixing architectures, with methods like QMix, QTrain, and WQMix, each proposing different solutions to this fundamental trade-off. Okay, now let's move to QMix. QMix represents one of the most influential solutions to the value function factorization problem. The key innovation is learning a monotonic mixing function that satisfies IGM while being more expressive than simple addition. The architecture consists of 3 main components. The first one is agent network. Okay, the agent network is where agent I learns its individual utility function, and these networks take local observations as input and output utility values for each possible action. The second is a mixing network that takes all agent utilities and the global state as input to produce the total team value Q. Third, a hypernetwork that generates the weights for the mixing network based on the global state. So the key constraint is monotonicity. The partial derivative of total Q value with respect to each individual Q value must be non-negative. So this mathematical constraint ensures the IGM property holds, guaranteeing that decentralized action selection leads to globally optimal behavior. And QMix achieved remarkable success on StarCraft 2 and became the foundation for many subsequent methods. It proves that with clever mathematical constraints, you can have both sophisticated coordination and decentralized execution. Okay? The second major approach within CTDE is Centralized Critic method. This approach takes inspiration from actor-critic algorithms in single-agent RL, but adapts them cleverly for multi-agent setting. Okay, the fundamental insight is to separate learning problem from execution problem. And during training, we can afford to use centralized critics that has access to the global information to provide stable learning signals. And during execution, we use decentralized actors that separate using only local information. Okay, this approach is particularly flexible because it can handle both cooperative and competitive settings. In cooperative settings, agents can share critics or use joint reward signals, and in competitive settings, each agent can have its own critic that accounts for opponent behavior. Okay, now let's see MADDPG, multi-agent deep deterministic policy gradient. Maybe it is perhaps the most influential centralized critic method. It extends the successful DDPG algorithm to multi-agent settings and demonstrates how centralized critics can solve non-stationarity problem. Okay, the architecture is also very simple. Each agent I has an actor that takes only the local observation as input, and this is what gets deployed during execution. And however, each agent also has a Q, Q value that takes the global state and all agents' action as input during training. The policy gradient for agent I, look at this. This equation. Notice that the critic uses global information, but the gradient is computed with respect to local policy. Okay, this is where the magic happens. By giving each critic access to everyone's action, the environment becomes stationary from each agent's perspective during training, and agent I's critic can predict the consequences of actions while accounting for how other agents behave. This eliminates the non-stationarity problem that plagued independent learning approaches. Okay, so MADDPG has been particularly effective in mixed cooperative and competitive scenarios and has inspired a lot of extensions and improvements, including methods that add communication, attention mechanism, and more sophisticated critic architecture. Okay, speaking of the third major direction within CTDE, which is focused on the communication mechanism, this approach recognizes that while agents must execute independently, they can still benefit from sharing information through learned communication protocols. Okay, the fundamental challenge is learning what to communicate, when to communicate, and how to use the received information effectively. Unlike human communication, which relies on predefined language or protocols, agents must learn these communication patterns from scratch through interaction with the environment. And the architecture typically includes message generation from local observations, message integration into decision-making, and differentiable communication protocols that can be learned end to end. The advantage of learned communication is that it can enable coordination patterns that would be impossible with purely independent execution while maintaining the scalability benefits of decentralized architectures. It's like having a team of players who can call plays and coordinate without needing a central coordinator. Okay, let's see the example. TARMAC, Targeted Multi-Agent Communication. It represents a sophisticated approach to learn communication that addresses a key limitation of broadcast-based communication. As the number of agents increases, broadcasting to everyone becomes inefficient and noisy. Okay, the architecture has four main components. First, signature generation, where each agent creates a signature vector from its local observation. The second, message generation, where agents create messages based on their local state and current situation. Third, the attention mechanism, which uses signatures to compute attention weights over received message. And finally, integration, where the weighted combination of messages is integrated into the agent's policy. Okay, the attention mechanism is where TARMAC shines. Instead of treating all messages equally, each agent computes attention weights based on the similarity between its own signature and other agents' signatures. This allows the agent to focus on communications from teammates who are in a similar situations or who have complementary information. Okay, and Tarmac has demonstrated strong performance in scenarios with large number of agents, showing that the learned communication can remain effective even as team sizes scale up. It's particularly effective in domains where agents have specialized roles but need to coordinate their actions. Okay, the fourth major direction with CTDE is attention-based method. This method takes inspiration from the attention mechanism that have revolutionized natural language processing and computer vision, adapting them for multi-agent coordination. The fundamental insight is that not all agents are equally relevant for every decision. Okay, consider a robot in a warehouse. For clearing avoidance decisions, it should attend closely to nearby robots while largely ignoring distant ones. For high-level planning, it might attend to robots in related task area while ignoring those in completely different sections. Okay, so the benefit is efficient processing without losing important details. It's like having a smart filter that automatically highlights what matters most in each situation, allowing agents to make better decisions with limited computational resources. Okay, now let's see MAAC, Multi-Actor Attention Critic. It demonstrates how attention mechanisms can be integrated into centralized critic method to create more scalable and effective coordination. The innovation lies in using multi-head attention within critics to focus on relevant agents when computing Q values. The architecture embeds observation action pairs into fixed size vectors and then uses attention mechanisms to determine each agent's influence on the computed Q values. Okay, here's how the architecture works. Each agent's observation action pair is embedded into a fixed size vector representation, and this embedding serves as the input to the attention mechanism. The attention mechanism computes weights that determine how much each agent should influence the Q value computation for a particular query agent. And finally, the attended information is used to compute more accurate Q values. Okay, the multi-head attention allows the critic to focus on different aspects of coordination simultaneously. For example, one attention head may focus on the nearby agent for collision avoidance, while another head focuses on agent with complementary roles for task coordination. Okay, so MAAC has demonstrated strong performance in domains with large numbers of agents and showing that attention mechanisms can enable effective coordination even as team sizes scale up significantly beyond what was possible with earlier methods. The fifth and the final major direction within CTDE is role assignment and hierarchical method. This approach recognizes that many coordination problems can be simplified by learning explicit role assignments or hierarchical structures. Okay? The fundamental insight is that team coordination often benefits from specialization. So instead of having all agents learn identical policies, we can have agents to adopt specific behavioral patterns or roles. This reduces the complexity of the joint policy space and makes coordination more interpretable. So the advantage is structured, interpretable, and efficient coordination through a reduced search space. Instead of learning arbitrary joint policies, agents can learn within the constraint of meaningful roles. So role assignment can be either static or dynamic. And dynamic role assignment is particularly interesting because it allows agents to adapt their roles based on the current situation. And the hierarchical method extends this concept by creating multiple levels of coordination. high-level coordinators might assign roles and set objectives, while low-level executors implement specific behaviors. This creates a natural divide and conquer approach to coordination. Okay, let's see ROMA, role-based multi-agent learning. It provides an elegant solution to the role assignment problem by learning a small set of role policies that agents can dynamically adopt. And the architecture consists of several key components. The first one is a small set of shared role policies that represent different behavioral patterns or strategies. The second is individual policies for each agent that capture agent-specific behaviors. Third is the role selection mechanism that allows agents to choose which role to adopt based on the current situation. And finally, a policy mixing mechanism that combines the individual and the role policy to produce the final action distribution. The key innovation is the dynamic role selection mechanism. Instead of having fixed role assignment, agent can switch between roles based on the current situation. This is implemented through a learned role selector that takes the current observation as input and outputs a probability distribution over roles. Okay, and so ROMA has several advantages. The first is it enables structured team coordination by providing high-level behavioral templates. And second is more interpretable than black box coordination method because we can understand what roles agents are adopting. Okay. Third, it can be more simple efficient because agents can share learning across roles. Okay. Now we reach our third paradigm, decentralized training and decentralized execution. I call this the every agent for itself approach, representing complete independence to maximize scalability. This paradigm eliminates all centralization, embracing a philosophy of complete agent independence. It becomes essential in several scenarios like massive scale system like the internet routing or sensor network and situations where single points of failure are unacceptable. And researchers have explored 5 major directions in this paradigm: independent learning, opponent modeling, game-theoretic method and meta-learning approaches, and distributed communication protocols. While DTDE sacrifices some coordination capability, it provides maximum scalability and robustness. It's particularly crucial for massive scale systems where centralized approaches will be computationally impossible or create single point of failure. The challenge is achieving effective coordination without any centralized assistance. It's like trying to coordinate a flash mob where everyone learns the dance independently and must perform it together without a conductor. Okay, let's start with the independent learning, the most straightforward approach within DTDE. The fundamental idea is elegantly simple too. Each agent runs its own single agent RL algorithm, treating other agents as a part of the environment. And for each agent's perspective, the other agents are just another source of environmental dynamics. And agent I observes the environment, takes actions, and receives rewards, and updates its policy using standard single agent RL algorithms like Q-learning or policy gradients. The fact that in the environment includes other learning agents is treated as just another form of environmental complexity. Okay, the key characteristics include the complete independence with no sharing of information between agents, environmental non-stationarity as other agents' learning changes the environment, and linear scalability where computational complexity grows linearly with the number of agents, and the implementation simplicity that makes it easier to implement and parallelize. But, however, the challenge is severe non-stationarity. As other agents learn and change their behaviors, the environment becomes non-stationary from each agent's perspective. This can lead to unstable learning, okay, or totally failure to converge. So we need to do some algorithm analysis like IQL with parameter sharing, independent Q-learning with parameter sharing. It represents one of the most successful applications of independent learning. Despite its simplicity, this approach has enabled breakthrough results in complex domains like star graph 2 and dot 2. The architecture is also simple. All agents use the same network weights, but each agent has its own experience replay buffer and observes its own experiences. And during training, each agent computes gradients based on its own experiences, but all gradients are applied to the shared parameters. Here's why it works so well. While agents learn independently, the shared parameters create implicit coordination. So when agent I learns something useful, like how to avoid particular type of obstacle, it modifies the shared policy. This means agent J automatically benefits from the knowledge even though it is learned independently. Okay, the mathematical insight is that parameter sharing acts as a form of implicit communication. Instead of sending explicit messages, agents communicate by modifying the shared policy. Okay, and the second major direction within DTDE is opponent modeling. This approach recognizes that while agents may learn independently, they can still benefit from explicitly modeling other agents' behavior and policies. The fundamental insight is that other agents aren't just random sources of environmental non-stationarity. They are intelligent entities with their own goals and strategies. By learning to predict their behavior, an agent can make better decisions and adapt to their strategies. The key characteristics include explicit modeling, where agents learn representations of other agent policies, predict capabilities to anticipate other agents' actions, and adaptive behavior that adjusts based on observed opponent patterns, and recursive reasoning that leads to I think that you think that I think scenarios. However, the challenge is just the computational complexity grows with the sophistication of the modeling. Okay, simple opponent modeling might just predict the next action, while sophisticated models may try to infer the opponent's goals, beliefs, or even learning algorithm. And the more sophisticated the model, the more computational resources are required. Okay. Now let's move to DRON, Deep Recurrent Opponent Network, provides a concrete implementation of opponent modeling that demonstrates both potential and the challenges of this approach. The architecture has two main components working together. The first one is an opponent predictor network that predicts the opponent's next action based on the current state and history. This is trained using supervised learning on observed opponent actions. And second, a policy network that uses both the current state and the opponent prediction as input to choose its own action. Okay, the key innovation is the explicit integration of opponent predictions into agents' decision-making processes. Instead of just reacting to what the opponent does, the agent anticipates what the opponent will do and plans accordingly. This enables more strategic and proactive behavior. However, DRON faces several challenges. First, the prediction quality depends heavily on the opponent's consistency and predictability. If the opponent uses a highly random or constantly changing strategy, predictions may be poor. Okay, and the second is the opponent might also be learning and adapting, which means the predictor must continuously update its model. Okay, so let's move to the third major direction within DTDE, Game-theoretic Method, which applies concepts from the game theory to find stable joint policy in multi-agent systems. The fundamental approach is to model the multi-agent interaction as a game and seek solution concepts like Nash equilibria, where no agent can improve its performance by unilaterally changing its policy. So this provides theoretical guarantees about stability and optimality under certain conditions. The appeal of game-theoretic method is their theoretical foundation. They provide principled approaches to multi-agent learning with well-understood convergence properties. And in certain classes of games, this method can guarantee convergence to stable solutions. And however, the challenges are significant. The first is computing equilibria can be computationally expensive, especially as the number of agents increases. And second, many games have multiple equilibria, and it's not always clear which one agents should converge to. Okay, so that's the thing. Let's take a look at Nash Q learning. Okay, Nash Q learning requires each agent to learn Q values for all agents. And this means every agent needs to track the value of every possible joint action, which immediately reveals a scalability challenge. The key innovation is in the update rule. Instead of using the standard max operator from single agent Q learning, Nash Q computes the Nash equilibrium at each state, okay, just as the Spellman update equation, where V value is the value of the Nash equilibrium at a state. So computing the Nash equilibria at each state involves solving a matrix game. Given the Q value for all agents, we need to find the mixed strategies that form a Nash equilibrium. This requires solving a system of linear complementarity problems or using iterative method like fictitious play. The theoretical appeal is strong. Okay, Nash Q provides convergence guarantees to Nash equilibrium policies under certain conditions. But however, the practical challenges are severe. First, the computational cost of computing Nash equilibria at each state is very substantial. Okay. Now let's move to the fourth major direction within DTDE, meta-learning, which focuses on learning to adapt quickly to new tasks, environments, or teammates. This approach recognizes that in many real-world scenarios, agents may be able to rapidly adjust to new situations without extensive retraining. Okay, the fundamental insight is to optimize for fast adaptation rather than performance on any single task. Instead of learning a policy that works well on one specific task, we learn initial parameters that can be quickly fine-tuned to work well on a variety of related tasks. The challenge is that meta-learning requires training on distribution of tasks or teammate types. This means we need access to diverse training scenarios that captures the range of situations the agent might encounter. And in practice, this can be very difficult to achieve, okay, especially in complex domains. Okay, now let's take a look at MAML for MARL. MAML adapted for MARL operates on two levels. The inner loop performs fast adaptation, where the agent takes a few gradient steps to adapt to a specific task or teammate type. The outer loop updates the initial parameter based on the post-adaptation performance across multiple tasks. Here's how it works in practice. During meta training, the agent is exposed to a distribution of tasks or teammate types. For each task, it starts with the current initial parameters and takes a few gradient steps to adapt to that specific tasks, and then evaluates its performance. The outer loop then updates the initial parameters to improve performance after adaptation across all tasks. The key innovation is obvious: finding initial parameters such that a few gradient steps can quickly adapt it to new teammates or tasks. And mathematically, we are looking for parameters that are in a good position in the parameter spaces, which is close to good solutions for a variety of related problems. Now, can you think of real-world scenarios where this rapid adaptation capability should be crucial? Okay, my expected answers may be ad hoc team formation or human-robot collaboration, such that. And these scenarios highlight why meta-learning is becoming increasingly important in MARL. Now the final major direction within DTDE is distributed communication, which enables local coordination between agents without requiring centralized coordination infrastructure. Okay, the fundamental instead is that while we can't have centralized communication, we can still enable local communication between nearby agents. This creates a middle ground between complete independence and centralized coordination. This approach is particularly relevant for applications like the maybe swarm robotics, sensor networks, or distributed computing systems where agents can communicate with nearby neighbors but not with distant agent or central servers. So the key challenge is designing effective protocols that enable coordination without global knowledge. Each agent only has local information about its immediate neighbors, but somehow the system must achieve global coordination through these local interactions. Okay? The beauty of this approach is that it can create emergent coordination patterns. Simple local interaction rules can lead to complex global behaviors, similar to how flocking behavior emerges from simple local rules about separation, alignment, and cohesion. The robustness benefits are significant too. If some agents fail or communication links are broken, the system can continue to functioning using the remaining local communication channels. This contrasts with centralized systems where the failure of the centralized coordinator can bring down the entire system. Okay? Let's see the neighbor-based information sharing, which is built around a communication graph that defines which agent can communicate with other. This is particularly based on spatial proximity, but could also be based on functional relationships or other criteria. The information sharing mechanism allows agents to share feature representations or observations with their neighbors. Each agent then performs local aggregation, combining information from its neighbors with its own observations. This can be done through simple averaging, weighted combination, or more sophisticated methods like graph neural networks that can process neighbor information more intelligently. Okay. Finally, each agent updates its policy based on the local aggregated information. The policy update is completely decentralized. Each agent makes its own decisions based on its local view of the world, enhanced by information from neighbors. So the key innovation is that this creates swarm-like coordination where agents share information with nearby neighbors, and simple local interactions can lead to complex global coordination patterns. Okay? Now let me bring together everything we've discussed today into a comprehensive taxonomy of MARL paradigms. Okay, this slide represents the complete landscape of approaches we've explored, organized by their fundamental design principles. Okay? Now that you have seen the complete landscape, let me pose a final challenge. If you were tasked with building a coordination system for 1,000 autonomous delivery drones in a city, which paradigm would you choose and why? Think about the constraints: real-time execution, limited communication, dynamic environment, and the scalability requirements. Okay, think about that. I think this discussion perfectly illustrates why understanding this paradigm is so crucial. The choice isn't just about which algorithm is best, it's about which approach best fits your specific constraint and requirements. Okay? Now for your homework this week, I want you to apply the concepts we've discussed today to deepen your understanding and develop your analytical skills. So the first one is choose one subclass from CTDE and one from DTDE. For each chosen approach, I want you to explain the core motivation. What fundamental problem is it trying to solve? How does it address the key challenges of the non-stationarity and scalability that we discussed? Then compare the representative algorithms in terms of computational complexity and coordination capability and scalability. Okay? The second is scenario design. This is where you get to be creative. Okay, you need to design a specific multi-agent scenario that could benefit from MARL. This could be autonomous vehicle coordination at intersections or any other domain that interests you. Then analyze which paradigm and subclass would be most appropriate. Consider factors like the number of agents, communication constraint, and need for coordination, and computational limitations. Most importantly, you need to justify your choice and discuss potential implementation challenges. This assignment will help you to understand not just what these algorithms do, but when and why to use them. Okay? Now let me give you an exciting preview of what's coming next. Now that we understand the fundamental architectures and design paradigms, our next lecture will explore the dynamic aspect of multi-agent learning, which is how agents actually learn and evolve when interacting with each other. You will see what is self-play training, what is policy gradients in multi-agent settings, and what is main field theory. And plus, we will have a live demonstration of multi-agent learning dynamics in action. You will see how different paradigms behave when agents are actually learning and adapting to each other. Next lecture will bridge the gap between the static architectures we've discussed today and the dynamic learning processes that make MARL systems come alive. Okay? I want to say thank you for your attention today. We've covered a tremendous amount of ground, from the theoretical foundations of centralized approaches to the practical realities of distributed systems. I think you now may have a comprehensive map of the entire MARL landscape. Now I'd love to hear from your question. What aspects of today's material would you like to explore further? Are there specific algorithms or paradigms that you think you would like to discuss in more detail? Or do you have questions about how these approaches might apply to your own research or projects? Remember, the field of MARL is rapidly evolving and new approaches are constantly being developed. This paradigm we've discussed today provides the foundation for understanding this new development and for contributing to your own innovations to the field. Okay, that's all. Bye-bye. See you next time.